Hello students, welcome to Rayat Shikshan Sanstha Satara, Rose project of 11th Science conducted by Yashwantrao Chavan Institute of Science Satara. We are studying topic number 6 from 11th Physics, Mechanical Properties of Solids. And in today's lecture, we are going to study this point, elastic modulus or modulus of elasticity. There are three different types of elastic modulus or modulus of elasticity related to each type of stress and strain. Let us see first modulus of elasticity, which is Young's modulus or elasticity of length. This modulus is related to change in length of the object like metal wire, rod, beam due to applied deforming force. It is defined as ratio of longitudinal stress to longitudinal strain. Let us consider this figure. In this figure, this is a metal wire and one end of the metal wire is suspended from the rigid support. So here is the rigid support. Now, let us consider here capital L be the original length of the wire and A be the area of cross section of the wire, where R is the radius of the metal wire. Now, a load means force is equal to mg is applied at the free end of the wire. Here the load is applied to the free end of the wire. Now, due to this, deforming force get applied to the wire in downward direction. And due to this deforming force, wire get stretched. That means it get elongates or extension is produced in the wire. So due to this force F, we see that in this another parallel figure, there is an increase in length of the wire or extension produced in the wire or elongation produced in the wire is represented by symbol small l. So here small l is the extension or elongation produced in the wire. Once the elongation produced in the wire is completed, then final length of the wire is sum of original length plus extension produced in the wire. So capital L plus small l is here final length of the wire when it is subjected to load. Now, when the wire is in its equilibrium position, let us write here equation for longitudinal stress, and it is equal to applied force upon area. Let us substitute in this equation of force, that is equal to mg, and that of area. We get equation of longitudinal stress as it is equal to mg upon pi r square. Let us also write equation for longitudinal strain. It is equal to change in length per unit original length. So here change in length will be final length minus original length or initial length. So L plus L minus capital L, we get change in length as small l and original length is capital L. So we get here equation for longitudinal strain as it is equal to small l upon capital L. Now Let us write the equation for Young's modulus Y, as it is ratio of longitudinal stress to the longitudinal strain. In this equation, substituting the equation of longitudinal stress and that of longitudinal strain, we get Y is equal to F into capital L divided by A into small l. Now again substituting in this equation, F is equal to mg and A is equal to pi r square, we get another equation of Young's modulus as Y is equal to mg into capital L divided by pi r square into small l. Now, let us write SI unit for Young's modulus. We know that strain has no unit and dimensions. So, Young's modulus have same unit and dimensions as that of the stress. So, its SI unit is Newton per meter square and dimensions are L raised to minus 1, M raised to 1, T raised to minus 2. Young's modulus indicates the resistance, means opposition of an solid to elongation or compression. It is useful for characterization of an object subjected to compression or tension, and it is the property of only solids, means it is defined only for solids. Now, let us see next point related to Young's modulus. Young's modulus is numerically equal to stress, which will double the length of wire. We have to prove this statement. So let us see the proof of this. Let here L be the initial length of the wire. Now, length of the wire is double to its initial length. Then, final length of the wire is 2L. Then, here change in length will be final length minus initial length. So, 2L minus L is equal to this capital L. Now, let us write here equation for longitudinal strain. As longitudinal strain is change in length per unit original length. So, change in length is capital L. Original length is also capital L. So, we get longitudinal strain is equal to 1. Now, we know the equation for Young's modulus. It is Y is equal to longitudinal stress upon longitudinal strain. In this equation, substituting longitudinal strain is equal to 1. So, on substituting, we get finally equation for Y is equal to longitudinal stress. And from this equation, we conclude that if the length of the wire is doubled, then Y is numerically equal to the stress. And here we complete the proof. And this is all about Young's modulus. Now, let us see the next modulus of elasticity, which is bulk modulus or volume elasticity. This modulus of elasticity is related to change in volume of the object or body due to applied deforming force. And this bulk modulus is defined as ratio of volume stress to volume strain. Let us consider this figure. In this figure, this is a sphere, and this sphere is made up from rubber. And this sphere, म्हणजेच ह्या डॉटेड सर्कलनी रिप्रेझेंट केलेला हा काय आहे, एक स्पियर आहे आणि तो रबर पासून तयार केलेला आहे. This sphere made up from rubber is completely immersed in a liquid. त्याला लिक्विड मध्ये completely बुडवला. Let here V be the original volume of the sphere. Now, when this sphere made up from rubber is completely immersed in liquid, then what will happen? That liquid will exert force on that sphere uniformly from all sides. म्हणजे ज्या वेळेस हा स्पियर लिक्विड मध्ये कम्प्लिटली इमर्स्ड असेल तर ते लिक्विड काय करेल, त्याच्यावरती सर्व बाजूंनी परपेंडिक्युलर डायरेक्शन मध्ये फोर्स अप्लाइड करेल, लाईक दिस. आणि त्या फोर्समुळे काय होईल की त्या लिक्विडच्या फोर्समुळे तो स्पियर युनिफॉर्मली कॉम्प्रेस्ड होईल, म्हणजे त्याची साईज छोटी होईल. मग या ठिकाणी आपण पाहू शकतो की ड्यू टू धिस फोर्स एक्झर्टेड बाय लिक्विड means compressive force, that sphere gets uniformly compressed from all sides. So this is the compressed sphere. Compress होणार म्हणजे काय होणार आहे, तर त्याची व्हॉल्यूम डिक्रीज होणार आहे. So let here dV be the decrease in volume or change in volume of the sphere. आणि ज्या वेळेस स्पेरिकल ऑब्जेक्टच्या व्हॉल्यूम मध्ये चेंज होतो त्याच वेळेस त्याच्या प्रेशर मध्ये देखील बदल होतो. सो या ठिकाणी व्हॉल्यूम डिक्रीज झाली म्हणजे प्रेशर काय होणार आहे, इन्क्रीज होणार आहे. आणि वाइस वर्सा, जर व्हॉल्यूम वाढली तर प्रेशर कमी होणार आहे. या ठिकाणी व्हॉल्यूम कमी होतीये म्हणजे प्रेशर, इनसाइड प्रेशर काय होणार आहे, वाढणार आहे. आणि त्यालाच आपण म्हणतो चेंज इन प्रेशर डीपी. So here dP is the change in pressure. Now let us write here equation for volume stress. As we know that volume stress is equal to applied force upon area, and that is equal to dP. We have derived this equation earlier in types of stress and stress. Now let us write equation for volume strain. It is change in volume per unit original volume. So we get here equation for volume strain, that is equal to minus dV by V. What is the meaning of here negative sign? Negative sign indicates that there is a decrease in volume of the body. Let us write equation for bulk modulus, as it is the ratio of volume stress to volume strain. So in this equation, substituting the equation of volume stress and that of volume strain, we get equation for bulk modulus K. It is equal to V into dP divided by dV. Now let us write SI unit for bulk modulus. We know that strain has no unit and dimensions. So bulk modulus has same unit and dimensions as that of the stress. So its SI unit is Newton per meter square and its dimensions L raised to -1, M raised to 1, T raised to -2. Bulk modulus indicates the resistance, means opposition of gases, liquids and solids to change their volume. Bulk modulus is maximum for solids and it is minimum for gases. Gases have two bulk modulus. First one is the isothermal bulk modulus and isothermal bulk modulus. K isothermal means isothermal bulk modulus is equal to P, means here P is the pressure of the gas. And second bulk modulus for gas is adiabatic bulk modulus. So K adiabatic is equal to gamma P, where gamma is equal to Cp upon Cv. And Cp upon Cv means it is the ratio of specific heat of gas at constant pressure to specific heat of gas at constant volume. As bulk modulus indicates resistance of gases, liquids, and solids to change their volume, so this bulk modulus is the property of gases, liquids, and that of solids. So this is all about bulk modulus. Now, let us see what is meant by compressibility. Compressibility is defined as reciprocal of bulk modulus of elasticity. So we have compressibility is equal to 1 upon bulk modulus. Let us write equation for compressibility. We know the equation for bulk modulus. It is K is equal to V into dP divided by dV. Substituting this equation in this equation, we get equation for compressibility as it is equal to dV upon V into dP. From this equation, we can write SI unit for compressibility as meter square per Newton, and its dimensions are L raised to 1, M raised to -1, T raised to 2. So this is all about compressibility. Now, let us see the third modulus of elasticity, which is modulus of rigidity or shear modulus or elasticity of shape. This modulus of elasticity is related to change in shape of the body due to applied deforming force, and it is defined as ratio of shear stress to shear strain within elastic limit. Let us consider this figure. This is a figure of cube. And in another figure, we have to consider only front face of the cube, which is A, B, C, D. And we know that in this figure, AB is the bottom layer, CD is the top layer, and capital L be the length of each side of face of the cube, means it is original length. Now, tangential force F bar is applied to the top layer CD. So here tangential force F bar is applied in this direction to the top layer CD, such that bottom layer AB is kept fixed. Now, what will happen due to this tangential force F bar acting on top layer CD? Top layer CD displaces to the new position C dash D dash through a small angle theta. And then there is a change in shape of face of cube, which is A, B, C dash, D dash. Now here, this distance D, D dash, C, C dash is represented by symbol delta L. And what is this delta L? It is called as relative displacement or displaced length of the top layer with respect to a fixed bottom layer AB. Now here, let us write the equation for shear stress. Shear stress is equal to tangential force upon area. So we get it is equal to F upon A. And we know the equation for shear strain, and it is equal to theta, and theta means angle of shear. So let us write here equation for modulus of rigidity, as it is ratio of shear stress to shear strain. So on substituting in this equation, the equation of shear strains and that of shear strain, we get equation for modulus of rigidity is equal to F upon A theta. Let us write the SI unit for modulus of rigidity. Strain has no unit and dimensions. So modulus of rigidity has same unit and dimensions as that of the stress. So its SI unit is Newton per meter square, and its dimensions are L raised to -1, M raised to 1, T raised to -2. This modulus of rigidity indicates resistance offered by solid to change in its shape. Means it indicates the opposition offered by solid to change their shape. So it is the property of only solids. Modulus of rigidity is the property of only solids. So this is all about modulus of rigidity. Now, let us see the next point, which is Poisson's ratio. Poisson's ratio is defined as within elastic limit, the ratio of lateral strain to the linear strain. Let us obtain here expression for Poisson's ratio. Let us consider this figure. Generally, when force is applied on a body in any direction, then there is a change in size of the body. The change in size of the body takes place in two directions. It takes place in two directions. First one, change in size of a body in the direction of applied force. And secondly, change in size of the body in a direction perpendicular to the applied force. Now, in this figure, this is a wire. One end of the wire is fixed to a rigid support. So this end is fixed to a rigid support. Let here capital L be the original length of the wire. So this is the original length of the wire. Now, this is the free end of the wire. And at this free end, a force or load F is applied. Okay. Now, let us consider here capital D. This total distance. This is the capital D, means original diameter of the wire. Here we see that force is applied at the free end of the wire, means that force is applied in a direction parallel to the length of the wire. Now, what will happen due to this force? Due to this force, wire gets stretched. It elongates or extension is produced in the wire. So let us here consider small l, this distance to this distance. Small l be the increase in length of the wire due to the applied force F. And we see that this increase in length of the wire takes place in the direction of applied force. See here. This is the increase in length of the wire. This increase in length of the wire takes place in the direction of applied force. So at that time, strain produced in the wire is called as linear strain or longitudinal strain. So here, linear strain or longitudinal strain is defined as the ratio of change in dimensions to original dimensions in the direction of applied force. It's called as linear strain. So here, change in dimensions is nothing but the change in length, that is small l, and original dimensions means original length, that is capital L. So we get here equation for linear strain as it is equal to small l by capital L. Now, here, due to applied force, when length of the wire increases, then we see that diameter of the wire also decreases. So here we see that when length of the wire increases, at that time, this is the decrease in diameter of the wire, small d. So this distance is nothing but what? Decrease in diameter of the wire. And we see that this decrease in diameter or change in diameter of the wire takes place in a direction perpendicular to the applied force. And at that time, strain produced in the wire is called as lateral strain. So here we define lateral strain as it is the ratio of change in dimensions to the original dimensions in a direction perpendicular to the applied force. So here change in dimensions means change in diameter to original dimensions means original diameter. So we get here equation for lateral strain, that is equal to small d by capital D. Now let us write equation for Poisson's ratio as it is. So Poisson's ratio, sigma is equal to, as it is ratio of lateral strain to linear strain. Substituting in this equation of lateral strain and that of linear strain. So we get equation for Poisson's ratio, sigma is equal to small d into capital L divided by capital D into small l. So this is the expression for Poisson's ratio, sigma. Poisson's ratio is the ratio of two similar quantities. Hence, it has no unit and dimensions. Theoretical value of Poisson's ratio lies between -1 to 0.5 and its practical value lies between 0 and 0.5. So this is all about Poisson's ratio.